In this program, we'll deal with the evolution of architecture, the restoration of old buildings and monuments, and textile architecture. Architecture was revolutionized by the appearance of the arch. The first to fully grasp the principle of the arch and to put to use its numerous possibilities were the Romans a few centuries before Christ. Ever since the Roman Empire, the technique is constantly being refined. Throughout the history of man, architects have wanted to erect monuments that defy the laws of balance. In architecture, the major challenge lies in the construction of a building's roof. In the case of cathedrals, for example, the aim was to make the roof as high as possible, so as to allow for a spacious and airy interior. The invention of the vault allowed some of those characteristics to be achieved. A vault is a stone structure in the form of an arc. In its simplest expression, it is semi-cylindrical. Such a vault is called a barrel or cradle vault. The cradle vault consists of wedge-shaped stones. Under their own weight, the stones are drawn downwards. However, due to their shape, they tend to squeeze one against the other. Each stone exerts a thrust on the stones next to it, which prevents them from falling. The stones hold each other up by compression. However, it is the keystone, that is the wedge-shaped stone closing the arch at its apex, which keeps the structure in balance. A cradle vault stones also exert a strong outward thrust against its supporting walls. That thrust is due to the pressure each stone exerts on the one beside it. To withstand that pressure, which tends to push them outward in an oblique direction, the walls have to be thick and solid, with as few windows as possible. Around the 11th century, the cradle vault was improved by placing two of them at a right angle and creating the groined vault. Groined vaults first appeared in Romanesque architecture, then re-emerged around the 17th century with the advent of classicism, largely inspired by Romanesque architecture. The intersection of the two cylindrical vaults forms four compartments. Projecting lines known as groins separate the compartments from each other. The groins come together at the keystone. It is the groins essentially which support the structure. They do this by concentrating the loads at four pillars or piers. If the piers are large enough, they can be used to support other groins. Arches like these can be juxtaposed to cover large surfaces. For example, they can be placed so as to form a cross, as in a church. Even if solidly buttressed by four piers, groined vaulting still tends to push its supports outwards. One way of absorbing the impact of that thrust consists in abutting a similar vault against it. This way, two equal and opposite thrusts meet at the pier common to both vaults. The two thrusts cancel each other out, thereby ensuring the structure's balance. Also, to contain the thrusts exerted on the back walls and sides of the structure, masonry piers called buttresses were built against the outside of the walls. The buttresses were placed opposite every row of interior piers. In their quest for ever loftier vaults, the architects developed the ribbed arch, also called the Gothic arch, because it's typical of Gothic architecture. The Gothic arch consists of two curved segments, which intersect to form a pointed arch. To build a ribbed arch, the four piers supporting the vault are brought closer together. Due to its arched shape and verticality, the Gothic arch exerts a very powerful outward thrust on its supporting piers. To counterbalance the thrusts, large flying buttresses are abutted against the church's outside walls. Flying buttresses are arches with an opening of 1/4 of a circle. They pass the load on to vertical buttresses, firmly anchored in the ground. In addition to their role as supports, flying buttresses collect rainwater, which they channel into pipes called guttering spouts. Buttresses and flying buttresses meant that the walls of Gothic churches no longer needed to be massive. They could be opened up and adorned with immense stained glass windows. For example, the Collégiale de Mantes, near Paris, was designed in classic Gothic style in the middle of the 12th century. By the end of the 19th century, metal became a major construction material. Unlike stone, metal has the advantage of withstanding tension, its use made for lighter structures. More recently, concrete revolutionized the principles of construction. Concrete gave rise to the emergence of an architecture on piles, which freed walls of their carrier function. Now, buildings rest on a series of pillars and beams. And with the pile system, the inside partitions can be placed exactly where they are wanted. The cathedrals of the Middle Ages and the Renaissance were erected at the price of incredible human effort. Some took 100 years to complete. The wear and tear of time, wars, and 20th century pollution are now threatening them. Fortunately, modern technology is able to come to the rescue of these monuments, which bear witness to our history. Many old monuments are suffering, ravaged by time, air pollution, and water erosion. The specialists are trying to save them through a variety of methods applied as gently as possible. To cleanse such vast surfaces as facades, the traditional method consists of running clear water over the stone. The water is allowed to trickle over the stones for varying lengths of time, from 1 hour up to several weeks. Eventually, the gentle washing carries off the dirt. It also dissolves the mineral salts that have crystallized on the surface of the stone. Severely damaged stone can become extremely brittle, to the point that at the slightest knock, it will crumble. This does happen to certain monuments. To cleanse a monument without damaging the stone, a new technology has taken hold: the laser beam. The laser beam is non-abrasive, since there is no physical contact with the stone. The sooty grime absorbs the laser beam and is pulverized. However, the naked stone underneath reflects the beam of energy. The surface that has been cleansed does not absorb the laser beam and is thus not touched. This process, relatively new to restoration, is an adaptation of a process used for some time, notably in medicine. The laser's light comes from a crystalline rod, whose end surfaces are perfectly parallel. The rod is placed between two mirrors. A light tube, producing very intense light, surrounds the rod. A brief but very intense flash of light excites some of the crystal's atoms. When they return to their normal state, the atoms produce photons, the particles that compose light. The photons are then relayed from one end of the rod to the other by reflection in the mirrors. This creates a surge of light waves, all identical in frequency and in perfect phase. When powerful enough, the light waves go through one of the extremities' semi-transparent mirrors. Lasers used in restoration emit extremely short impulses of about 1/1000th of a second. The brevity of these impulses prevents the material from heating up, but concentrates an enormous amount of energy, namely 100 megawatts per square centimeter. When the laser beam strikes the stone, the impact is so powerful that the layer of grime breaks away and is reduced to powder. The high degree of precision and selectivity of this process makes for good speed of execution. Cleansing a sculpture the size of a human face can be done in 10 minutes. It is also an effective means to restore stained glass windows and oxidized metal parts, such as gratings and statues. Stones, however, when too badly damaged, have to be replaced. Each stone is first drawn on paper, then removed from the wall. It is then measured very accurately, to the millimeter. From these diagrams, new stones are cut. Ideally, the replacement stone will come from the same quarry as the one used to build the monument. The rough stone arrives at the studio in huge blocks, several cubic meters in size. The blocks are dressed by machine into smaller chunks. Stone cutters then shape each new stone by hand, making them identical to the drawings made on the site. Taken back to the site, the newly cut stones are put into place. They are then sealed with mortar. Another technology enables specialists to measure the damage done to the structure of some buildings over time. It is known as photogrammetry. After demarcating the structure to be studied, photographs are taken. The structure is photographed twice, from slightly different angles. Measurements are also taken between various points of the structure. Each pair of photographs is then examined by stereoscopy in a laboratory. This is done with a device that has two eyepieces and is called a stereo comparator. The operator sees the structure of the object photographed in 3 dimensions. He studies that virtual model and measures it according to the 3 dimensions of space. A 2-dimensional projection can then be created on a computer and relayed to a plotter. This representation allows the experts to analyze the architectural object in minute detail and, for instance, to visualize any deformities in its structure. Photogrammetry enables us to commit our architectural heritage to memory and to ensure its preservation. For the past 30 years or so, daring architects have been exploring the ethereal and soft shapes of canvas constructions. New textiles made of extremely resistant synthetic fibers have allowed them to create works which would have been unthinkable just a few years ago. Today, architects are seeking to free forms and to lighten and brighten them. Various new materials are enabling them to do so. One example of the trend toward light, flexible forms is the textile structure, generally a partial shelter. Textile structures are used, for example, to cover the parvis of monuments. They may also be used in the building of completely closed structures. A textile structure is essentially a fabric membrane stretched over a metal framework. An assortment of poles, beams, arches, and metal cables form the frame. The fabric membrane is laced onto the frame with polyester rigging and elasticized cables. Its stiffness and stability come from a process called opposite double curvature, a curvature present at all points of its surface. An upper network of downward curved fibers perpendicularly crosses a lower one which is curved upward. The first pulls the fabric downwards, while the second tends to hoist it upwards. It is the equilibrium between these opposite tensions that ensures the fabric's stability. If a fabric's fibers were curved only in one direction, as in the case of a boat's sail, the membrane would not keep its shape. The slightest gust of wind would make it swell. Opposite double curvature allows the membrane to withstand the wind's uplifting effect. At the same time, the double curvature will counter the weight of snow, which tends to drag the membrane downwards. However, the stability made possible by the opposite double curvature only occurs when the fabric's fibers are stretched taut. The fabric must therefore be stressed by cables held in position at various points, such as vertical walls or masts. The commonest material used to make the membrane is a woven polyester coated with polyvinyl chloride, or PVC. The polyester molecules are produced by a chemical reaction between an organic acid and an alcohol. They are linked in long chains called polymers. These chains are then stretched to acquire a certain resistance. While extremely light, vinyl-coated polyester presents a resistance of about 11 tons per meter. In time, this material will trap dirt, but it has good durability and will generally last from 15 to 18 years. Teflon-coated woven glass fiber is another material with even more interesting properties. Stiffer than polyester, the glass fibers give the membrane its stiffness and resistance to stretch. Indeed, they have a warp elongation of 2%, whereas polyester is much more flexible, with a warp elongation of 12%. Teflon is a plastic used as a coating for a number of kitchen accessories. It adds to the textile membrane's durability, as well as to its resistance to heat and water. Teflon's qualities can be attributed to its chemical structure. It is composed of a chain of carbon atoms to which fluorine atoms are linked. Since the fluorine atoms are much larger than the carbon ones, they form a protective casing around the carbon atoms. Furthermore, the bonds between the carbon and fluorine atoms are very strong and stable. This atomic structure makes Teflon extremely heat resistant and chemically inert. Teflon also prevents dust and dirt from penetrating the weave and makes the fabric virtually self-cleansing under the effects of wind and rain. Finally, Teflon-coated glass fiber fabric reflects almost 75% of the sun's heat and light. It therefore provides excellent thermal insulation and is translucent enough to provide sufficient natural lighting inside. Its only drawback is that it is very expensive. textile structures can take on any shape a supple fabric can be made to take. These figures are combinations of cones, spheres, or cylinders. In their quest for new shapes, architects and engineers are now using computerized systems. Computerized systems enable them to design forms that will cause fabric the least stress and distribute that stress evenly over the whole surface. With its detachable and light structures, modern textile architecture is reminiscent of the Amerindian tents that inspired it. Animal hides, natural fibers, synthetic fibers, the fabrics evolve, but one architectural obsession remains unchanged: the quest for beauty and lightness.